For decades, dark energy has been called the greatest mystery in the cosmos, the invisible pressure accelerating the expansion of the universe. But what if the foundation is flawed? What if dark energy is not a force at all, but a misunderstanding of what the universe is actually doing? New measurements, growing tensions in astronomy, and cracks in the standard cosmological model suggest something profound. Scientists may have gotten dark energy wrong from the very beginning. If you enjoy calm, deep explanations of real space science and the mysteries still unfolding, make sure to subscribe because this story is far from over. The discovery that created dark energy. Dark energy entered cosmology through one of the most shocking discoveries of the 20th century. In the late 1990s, astronomers were studying distant Type 1, a supernova, exploding stars so consistent in brightness that they can be used as cosmic distance markers. Researchers expected these supernovae to confirm what gravity predicts. The expansion of the universe should be slowing down over time. Matter attracts matter. Gravity pulls everything inward. The farther the universe expands, the harder gravity should work to slow it. But the observations revealed the opposite. Distant supernovae appeared dimmer than expected. The universe was not slowing down, it was expanding faster. Expansion was accelerating. This result was so unexpected that scientists initially suspected error. They recalibrated instruments, rechecked dust models, challenged their assumptions. But the acceleration signal persisted. The universe seemed to be speeding up, driven by something beyond ordinary matter and gravity. To explain this, cosmologists introduced a new term into the equations: an unknown energy embedded in space itself, exerting negative pressure, pushing the universe outward. They called it dark energy. Within a few years, it became one of the most dominant components of the cosmic inventory. But this is where the first problem emerges. Dark energy was not discovered in the way planets or galaxies are discovered. It was inferred as a solution to a mathematical and observational mismatch. Dark energy was always a placeholder. Dark energy is often discussed as though it is a physical substance. But in truth, no one knows what it is. It has no confirmed particle, no confirmed field, no known interaction other than its gravitational effect on the expansion of space. The most common version of dark energy in cosmology is the cosmological constant, an energy density of empty space that remains fixed over time. Einstein originally introduced it to keep the universe static, then later called it his greatest mistake after expansion was discovered. Ironically, cosmology revived it decades later as the simplest explanation for acceleration. But the cosmological constant creates one of the greatest theoretical catastrophes in all of physics. Quantum field theory predicts that empty space should contain enormous vacuum energy. When physicists calculate this vacuum energy, the result is absurdly large, wrong by a factor of 10 to the power of 120 compared to what is observed. This is not a small disagreement. It is the largest mismatch between theory and observation in the history of science. If the cosmological constant is truly dark energy, then our understanding of quantum physics is missing something fundamental. Or dark energy is not vacuum energy at all. Either way, the concept is not settled. It is unstable. In that sense, dark energy has always been a placeholder, a name for whatever we do not yet understand about cosmic expansion. The universe's expansion rate does not agree with itself. In recent years, the dark energy problem has deepened into what many call a full crisis. The expansion rate of the universe is measured by the Hubble constant. But today, different methods of measuring it produce different answers. If scientists measure expansion using the early universe by studying the cosmic microwave background radiation left over from the Big Bang, they get one value. If they measure expansion using the nearby universe through Cepheid stars and supernova, they get another, larger value. This discrepancy is called the Hubble tension, and it is not going away. The significance of this tension is enormous because the standard cosmological model assumes dark energy behaves smoothly and consistently across cosmic history. If the expansion rate is inconsistent, it suggests that something in the model is missing or misunderstood. The universe may not be expanding the way we think it is, and if expansion is misunderstood, then dark energy, created to explain it, may also be misunderstood. What if acceleration is not what we think? One possibility Gaining attention is that cosmic acceleration may not be as straightforward as the standard model assumes. The universe is not perfectly smooth. It is a vast cosmic web of dense galaxy clusters, enormous voids, and filamentary structures spanning billions of light years. Light travelling across the universe does not move through uniform space. It passes through warped gravitational landscapes. It bends. It stretches. Its path is influenced by massive structures. Distance calculations assume the universe behaves homogeneously on large scales. But if that assumption is wrong, even slightly, then the supernova measurements that revealed acceleration might be distorted. The acceleration signal could be partly an artifact of interpreting a complex cosmic structure through simplified models. That would mean dark energy is not a force pushing outward, but a misunderstanding of how cosmic geometry affects light and distance. What if gravity itself changes at cosmic scales? Another profound possibility is that dark energy is not needed because gravity itself is incomplete. Einstein's general relativity has passed every test within the solar system and around black holes, but cosmology applies it across unimaginable distances and timescales. Some alternative theories suggest gravity behaves differently on the larger scales. Perhaps it weakens, perhaps it evolves, perhaps the equations change when applied beyond galaxy clusters. If gravity behaves differently across cosmic distances, then the universe could appear to accelerate without requiring dark energy at all. This would not be unprecedented. Newton's gravity worked perfectly until it could not explain Mercury's orbit. Einstein replaced it with a deeper theory. Dark energy may represent the next boundary, where our understanding of gravity breaks down. New observations are making. Dark energy, harder to defend cosmology, is now entering a period that feels strangely familiar in the history of science. Dark energy has existed for decades as the easiest explanation for the accelerating universe. But the deeper scientists look, the more unstable the idea becomes. Modern telescopes and sky surveys are not producing comfort. They are producing tension. Some measurements suggest dark energy behaves like a constant background force, while others hint it may evolve over time. The more precise the instruments become, the more the universe refuses to fit neatly into the simple story dark energy was meant to tell. Why dark energy has never been directly measured. One of the most unsettling facts is that dark energy has never been observed as a physical thing. It has no confirmed particle, no laboratory detection, and no known interaction beyond its effect on expansion. Every piece of evidence depends entirely on indirect inference, on distance measurements, gravitational modelling, and assumptions about cosmic uniformity. That means dark energy is not proven in the way matter or radiation is proven. It is a name given to the unknown factor required to make the equations match what we see. The Hubble tension is a warning signal. The universe's expansion rate should be consistent across methods, but it isn't. Measurements from the early universe disagree sharply with measurements from the nearby universe, creating the unresolved Hubble tension. This is not a small statistical glitch. It is a growing crack in the standard model. If dark energy were truly simple and constant, the expansion history should align. The fact that it's not suggests that either we are missing physics or dark energy is not the correct explanation. Dark energy might be a placeholder for multiple unknown effects. Some researchers now suspect dark energy may not be one phenomenon at all. It could be an umbrella term covering several missing pieces: cosmic structure distortions, incomplete gravity, observational bias, or unknown fields. In that sense, dark energy may represent not the greatest discovery of cosmology, but its greatest gap. The concept works mathematically, but the universe may be telling us it is only a temporary patch, not a final answer. Why the universe does not behave as the standard model predicts dark energy is supposed to be smooth, consistent, and simple. Yet the universe appears more complicated. Galaxy clustering patterns, expansion measurements, and cosmic history hints do not always align cleanly. The deeper the data becomes, the harder it is to pretend the model is complete. These inconsistencies are exactly how scientific revolutions begin, not with dramatic announcements, but with small mismatches that refuse to disappear. The real possibility, dark energy, may point to new physics science has faced this before. Epicycles once explained planetary motion. Ether once explained light. Both were replaced by deeper truths. Dark energy may follow the same path. It may not be the engine of expansion, but the signpost pointing toward a new understanding of space, time, and gravity. If that happens, it will not mean scientists failed. It will mean the universe forced us to evolve our thinking again. Dark energy has shaped modern cosmology. But the deeper scientists investigate, the more cracks appear in the story we thought was complete. What began as a simple explanation for cosmic acceleration has become one of the greatest unsolved problems in physics, raising questions about gravity, space-time, and the true structure of the universe itself. If you enjoyed this calm deep dive into one of the most important mysteries in science, make sure to subscribe and turn on notifications. We explore the universe as it truly is, uncertain, evolving, and full of surprises. Thanks for watching, stay curious, and I'll see you in the next video.